All right, so let's start out with a little bit of statics review. We're going to use a ton of statics in this class, so hopefully you're pretty solid, and if not, hopefully you can get pretty solid pretty quickly. But these are some basics that we'll be using that you should be able to carry over, whether you had statics recently or it's been a while. This is a review, and there's also homework for this review as well, our homework number 1. So looking at vectors, vectors are massive. When we have a vector, they have both magnitude and direction, and often we want to resolve the vector into an x and a y component. So for example, what we see here is like my pointer, what we have is like a 50 Newton vector at an angle of 20 degrees, and I want to resolve it into an x and a y direction. In essence, there's the two ways you can really do this is one, just take the cosine for the x component and sine of that angle for the y component. Now, if I'm doing that, two things I got to watch out for. One is that this angle 20 degrees is from the x-axis. And you could derive these. This is from, SOHCAHTOA, cosine opposite over hypotenuse, and cosine adjacent over hypotenuse, sine opposite over hypotenuse. But regardless, you do have to be careful, because what we have here is a negative x direction for our component. So how do I get that in there? Well, one way I can do it is I just add it. I just put a negative in here. The other option is I resolve that angle all the way to the positive x-axis, which would be the angle here, which would be 180 minus 20, or 160 degrees. This would give you the sign automatically. However, I'm a much bigger fan of just looking at it and figuring it out. I think knowing that it's in the negative direction, just putting in the negative, is much more efficient. Another thing we'll use often is if I know the distances in the x and y direction, and I have a vector in this case, or I know the relationship between the x and y. The way I do this is I take the magnitude of the vector, 50, and I just multiply it. If I'm with the x, I'm just taking the distance in the x over the hypotenuse, 4/5, right? Because 4/5 is the cosine of the angle, right? Cosine of that theta would be the adjacent over hypotenuse. Once again, I would need to put in my negative sign. I don't know why it's not there, but yeah. And then for the y direction, you just do the y distance over the x. So after that, we should definitely be familiar with particle equilibrium. Some of the forces x equals 0, some of the forces y equals 0. And let's take a look at an example of how I would use that particle equilibrium with this object with 3 forces on it, a 10 Newton, 20 Newton, a 50 Newton. And I want to resolve that into some single force that would give me equilibrium. So what I would do is I would say that the total net force, or sum of the forces in the x, must be equal to 0. So just putting into the components from what we just learned about resolving our vectors in the x direction, I have 10 times the sine of 20 degrees. The reason it's sine is because now our angle is to the vertical, and I want the horizontal, and it's going in the positive. So the way you can think of this is the component would be pointed this way in the x direction. And then same idea with the 50. It's also in the positive, so I'd say plus 50. Now I have a distance of 4, and this is the classic, you'll see this all the time, 3, 4, 5 triangle. So 4/5 is my x component. No, I'm changing colors here. There we go. And then I have the 20 going the other way. So I have a negative 20, nothing to resolve there. It's all in the x direction. And then I have some other resultant force x. That's what I'm trying to find. So could have probably started with that, but punch that all in my calculator. And I ended up with a negative 23.42 newtons. And same idea in the y direction. Let's go ahead and start with it. I think it looks cleaner like that, right? So we're trying to find this Fy, this resultant force in the y. Maybe I should call it Ry, but regardless. So then I have the 50 Newton force as a component. It's pushing up of 3/5. I have the 10 pointed down. Now it's the cosine of 20 to get that vertical going down. The 20 Newton doesn't do anything because it's all in the x direction. So we set that equal to 0, and I end up with an Fy of negative 20.6 newtons. Or what I can say is it's 20.6 newtons pointed down. As long as I know what it means, you could probably do either one. And then you could resolve it into a single force. It does say what single force, so I guess I should do that last step. So the last step, adding these together, I have 23.42 pointed to the left, and then I have this 20.6 pointed down. So then my resultant force starts where the vector started, ends where it ends. That's my resultant, and that resultant using Pythagorean is just equal to the square root of 20.6 squared plus 23.42 squared. I'm going kind of quick, so it looks a little bit messy, but hopefully you get the idea. Pretty easy math here. 31.19 newtons. And then because it's still a vector, I need some sort of angle here. So I would probably say, well, let's find this angle from the axis theta, right? Well, I know that using my my trig functions, the inverse tangent of that is opposite over the adjacent 0.42. So I ended up with an angle of 31. I believe 41.33. I might have to check this. 20 and 23. I think it's 41.33 degrees. Yes, it is. I had something a little goofy in my notes, but that's what it is. So the final answer would be like 31.19 newtons at an angle of 41.33 degrees. And then I would want to give a reference point. So that's from the positive x. So I would probably report something like that guy for a final answer. And yeah, there we go. Not too bad. All right. Moving on. So this is particle equilibrium, meaning it's just a single particle when we add up all our forces. We also could have a rigid body equilibrium. So as we see the example now, we're talking like beams or structures or machines or anything like that, where there's a rotational component. Really what we're adding here is the moment. Because now there's a rotation that can happen as well. Well, not actual rotation because we're in statics, so nothing's actually moving, but rotational force. So looking at an example, how we would use these three equations, I have this beam A, B, C, D that's supported at A and D, and it's being pulled on by a cable at C, which is supporting this other beam. E doesn't have a letter down there. I guess I could call it F or anything else, which is a distributed load of 20 pounds per foot. And there's a point load of 600 pounds up top. And we want to find the tension in the cable and the three different reactions. So the way I would do this is free body diagrams are always key. So a free body diagram, we're just going to represent this object. Let's start with the lower piece. So maybe I should make a note of that. This is for the lower. And put all of my forces on there. So what do I have on the lower? Well, I have an EY. I could put an EX. It's going to be 0. There's no X forces. And then I have some sort of tension over here. And then I have this distributed load pushing down, something like that there. And what is that equal to? 20 pounds per foot. So there's three unknowns. Anytime I have three unknowns, I can solve it using statics. Like I said, if we were sum the forces in the x, we'd see that EX is equal to 0. What else do I want to do here? Well, I can't sum the forces in the y because I have two different forces in the y. You could, because you could just say it's symmetric. In fact, that's probably what I would do and say half the load goes to one side and half the load goes to the other. As a reminder, this is a 5-foot beam at 20 pounds per foot, so it has a total force down of 100. So it's going to be 50. As an alternative, I could also sum the moments about either side. Let's sum the moments about point E, set it equal to 0. Counterclockwise being positive is my normal sign convention. I think that's pretty much everyone's sign convention, but some people like to be different, I guess. I lost my T. So from here, what do I have? I have the T with a lever arm of 5 feet minus this 20 pounds per foot times 5. And it acts, of course, right at its centroid, which is 2.5 feet away from point E. Set that equal to 0. And I get a total tension of 50 pounds. And like I said, you'd also get that just from symmetry. And then from our summing the forces in the y direction, we have EY going up plus this 50 going up minus this 20 times 5, which is 100. So then my EY would be equal to the other 50 pounds, both positive, both going up, all that good stuff, right? So there's two things we were looking for. That's all I can really do with that part. Then I could do a free body diagram of the top part. That was supposed to be in black. Red is very angry, loud. Let's do that again. something like that there. So if I look at the forces here, what we have is at A, we have a pin, so I could have an AY, an AX. I have the 600 pounds, which is maybe here, 600. I have the cable at C. Well, that also is pulling down, and I know that that's equal to the tension, which is 50 pounds. It's like an equal and opposite. If this is pulling up here, it has to be pulling down over on the other side. And then I have dy as a roller, so it just has a y component pushing up. So once again, three unknowns, three equations. I can solve for everything. Start with the easy one. Sum of the forces x equals 0. We know ax is 0. From our summing the moments about point A is equal to 0, counterclockwise being positive. I would have what? dy. What's the top dimensions? I have 6 plus 3, which is 9. Minus that 600 pounds, its lever arm is 3. And then minus the 50. And hopefully you're clear with these signs. Minus, not because it's pointed down, because it's making a clockwise rotation about point A. Minus 50 times 5 equal to 0. So that gives me a reaction at D of 227.78 pounds, according to my notes. Hopefully I plugged it into my calculator right. And then what else? I still need to know AY. So from our sum of the forces in the y equals 0, AY going up, minus 600 going down, minus 50 going down, plus that 227.78 going up is equal to 0. So I get a reaction at A of 422.22 pounds. Ooh, something like that, right? Cool. All right. So another thing we should be familiar with is what's going on internally in members. So what does the internal shear force or internal moment look like on a member? And here I see something where there's a beam, there's two forces on there, there's a reaction, it's a rigid support. And I'm trying to find those internal shear B and moment at that point being. I don't know. We're going to talk about sign convention when we do shear and moment diagrams. But for right now, we're just drawing it whichever direction. But regardless, here's an example. Let's say we had this this object, this C shape, and we had a tension of 850 newtons, and we wanted to find the internal forces at point J. And the idea is I'm going to cut it at point J to figure out what's going on. So I could look at either the upper half or the lower half. You'd get the same numbers regardless, but we always want to start with some sort of free body diagram. So I'm going to draw a free body diagram of that upper half. So it goes over like here, maybe to here. And then I have my force of the cable, which was 850 newtons. And then internally, I have some sort of shearing force, which we're calling V. I'll call it VJ because it's happening at the point J. I have a vertical or a axial force, which I'm calling JY, and I have a moment at J. So those are my three internal forces I can have. To solve for those, I start by summing the forces in the x direction equals 0. To put this 850, I need the x component. To do that, what I'm going to do is draw like a triangle here. And looking at my dimensions, this is 300 tall. And what is this? 160, because that's 280 minus 120 to give me just the dimension along here, right? To make that triangle. And that hypotenuse, if I did my math right, I got 340 millimeters for that. So when I take that 340, or sorry, that 850 and want to put it into component form in the x direction, I go the x distance, 160 over the hypotenuse, 340. And because it's pulling to the right, they would have a positive x component. So we're good there. And then I have the Vj, so minus Vj is equal to 0. So from that, I get the shearing force at J to be negative 400, or I'd probably just say 400 newtons. And the direction really isn't that important because if I were to do a free body diagram on the bottom half, that direction would flip. It'd be pointing to the right. It's like an equal and opposite thing, right? And in this class, when we look at the material strength, all we usually care about is the magnitude. I guess bending we do care about because we need to know tension versus compression, but we'll get to all of that exciting stuff later. Meanwhile, some of the forces in the y direction, we can get that J, our axial force, minus this 850. Same idea. We only want the vertical component, which is 300 over 340. Set that equal to 0, and I have an internal axial force of 750 newtons. This one would be going like upward, or in compression is probably what I'd say. But we're not worried about that yet. And last but not least, I would sum the moments about J is equal to 0. Sticking with my counterclockwise is positive convention, and that's the way I have it drawn. So I have this thing drawn as counterclockwise. So MJ is positive. And then I have that 850. Well, the 850 has two components that are creating a moment, because I have a vertical one with its lever arm and a horizontal one with its lever arm. So let's start with the horizontal, with this guy here. So I have to say, well, that's going to create a negative moment, and its magnitude is 850. To get the horizontal, I have what, 160 over 340. Then I need its lever arm. Don't forget its lever arm, or its distance vertical, because remember, if it's a horizontal force, we have a vertical distance, R cross F, all that good stuff. That distance is, at this cut, would be 100 millimeters down. So we have 100. And then I have the other component to that 850, which is also creating. So if I pull down, it's going to want to also create a clockwise or negative moment about J. To get the vertical component, we have, what's the vertical distance? 300 over 340. And then once again, I need its lever arm, or its horizontal distance over there, which would be what, 120 it looks like, because we're putting it right there, right? And I'm 120 away. Set that whole thing, whoa. Oh yeah, set the whole thing equal to 0. We're good, we're good. Solve for MJ, and I got an MJ equal to 94,000 Newton millimeters. And I could show direction, since I did with the other. What's going on with my pen? There we go. So because we said that counterclockwise is positive, if you punch all that into your calculator, of course, you're moving the negatives to the other side, so you end up with a positive. So those would be my answers for that guy. Cool. So those are internal forces. The next question is, well, if I know internal forces, I want to put the whole thing together in something called a shear and a moment diagram. And there's multiple ways you can do this. Method of sections. You can come up with equations and do integration. I have my particular way of doing it, and it all has to do with this relationship between the three. If I have a point load, then that point load will become, in essence, like a flat line, because we're moving up in power. Because if you integrate your load, you'll get shear. If you integrate your shear, you'll get moment. And then that flat line, if I integrate it, I get its line with a constant slope, or a straight line. Well, same idea with an evenly distributed. Now I'm going up a level. So I'm starting with a flat line. So I have a line with a constant slope, which means I need some x squared or a quadratic. Oh, and I forgot to mention the areas are key. So the area is equal to change. So the area underneath the shear is equal to the change in the moment. And the area under here, because it's negative, it brings it back down, something like that guy there. Yeah, and so on and so forth. So there's a basic equation, but let me just show you through an example how I do it. It's probably the easiest way. The first step is to find those reactions. So we have a by. There is no bx. You could sum the forces in the x and show that, but there's no x force. There's no bx. Regardless, so if I look at those reactions, I would start by summing the moments about point B and set it equal to 0. Once again, counterclockwise is positive. So I have, let's see, EY. On the far end, its distance away from B is that 12 plus 12 plus 12, which is 36. And then I have minus these two 125 forces. So 125 times 12, and minus the other one, 125 times 24. And then I have the distributed load, which is also going to create a clockwise, sorry, counterclockwise, a negative or positive moment. Oof, even I'm getting tripped up. That last one, I don't quite ever want to move it down a line, plus that 20 pounds per foot over 9 feet, that's its magnitude. And then, of course, at the centroid, that's 4.5 feet away. Set the whole thing equal to 0, and I can find the reaction at E to be 102.5 pounds going up. Then I can sum the forces in the y direction equals 0, and I have By plus I have this 102.5 that I just found. So putting on my positives at E. And then I have minus this 20 times 9 for the distributed load, minus those two 125s. Set that equal to 0. And I have a reaction at B of 327.5 pounds. Cool. So let's put these in here. So this is what? B is 327.5. E was 102.5. Then what I do is I draw like a reference line. So we call these inflection points, or anywhere where it's going to change, but really it's at any place there's a support, beginning and ending of loads, I mean, anytime that there's something interesting happening. So something like that. Let's get one at the very end here. Cool. And then I draw a horizontal line for my shear. So this is shear. I put my unit in here. These are pounds. And the way I do this is I start at the very end and I say, is there a force right at A, a shearing force, meaning a vertical force? There is not. I mean, there's a distributed load, but it hasn't really started yet. It's as I move to the right, it's going to start. So I start at 0. I'm doing purple so it'll stand out. And then it changes by the area. Like we said, change, area is equal to change. So 20 times 9 is 180. Now it's pointed down. So I'm going to say minus 180. And I normally don't put it actually in there because it gets kind of crowded. But that means by the time I get to B, I have to go down by minus 180. And then how do I get there? Well, like we said, the relationship is if this is a flat line, this has to be a straight line. No curve to it or anything like that. Then after that, I say, well, I have 327 going up. So I start with negative 180. I add 327.5, and I'm going straight up at that point. That brings me up to, look at my notes here, 147.5. And then nothing happens until I get to that 125 going down, which brings me down to 22.5. That's a 2. And then I keep going over until I go down another 125, which brings me down to what? Negative 102.5 minus 102.5. And then nothing happens until I get to the end and it says go up by 102.5, bringing me back to 0, which probably means I did something right. Regardless, so let's move on to the moment. Start with my reference line. These are in pound feet. And once again, area equals change. So I'm going to find the area here. Let me just look at my notes. I have minus 810. And I'm getting that because it's a triangle, 1/2 the base times the height. So what this is 1/2 9 times 180, negative 180. That's why I got negative 810. Not real clean, but well, my next segment is positive. The area is 147.5 times 12, which is what, 1770. My third area is also positive 270. And I am breaking it right there for those areas. And the last one is below this reference point. So I have a negative 1230. So put a little thing on that. And you can shade it if you want to make it look a little better, whatever your artistic inner self tells you. So just like before, we start off, is there a moment at the very end? No, there isn't. So I start off at 0 right here. And then I change by the magnitude. Well, I'm changing by negative 810. I didn't make this line. Let me make this line a little bit bigger. Let's say this is like negative 810. Well, how do I get there? Well, because this is a line of constant slope, now I have an x squared function, which really means I have two choices. Either it's got to be like this way, like convex, or this way, like concave. And how do I know? Well, I know because this distance here is actually the slope of the line. And what it means is if I ever cross that reference point, that means I have 0 slope. 0 slope's like horizontal, right? So it means it actually is this one that starts off and the slope's getting bigger and bigger and bigger as I move over. All right, so as negative 810, then I'm going to add in this 1770, and that brings me to 960. Where am I going to put that? Let's do it like right there. I already made a little mark there. 960. How do I get there? Well, because I had a flat line before. This is a line with a constant slope. Now I'm going to go an additional 270 to that guy, which would be 960 plus 270. What do I get for that? 1230. And then I have negative 1230, once again, a flat line. So this would just go straight back down to 0, which means I probably did something right. And that's my moment diagram. Cool. Sharing moment diagrams. All right, last but not least, centroids and moment of inertia. Normally notes won't take this long. This is an unusual one because I'm trying to cover a whole semester of statics in one talk, everything that's important, I guess. But so how do you find the centroid and moment of inertia of a shape? We'll need to know this when we talk about bending stresses, because it'll depend on where it turns from tension to compression and also how strong the material is, because a moment of inertia is like a resistance to bending. So when we talk about the bending of a beam or something like that, we'll see that in a little in a while. But if I have a composite shape, meaning I have 3 different shapes that I see up top right there, I guess I can point a different color, like the black. Oh, I can go to my pointer. I have 2 equations, x bar, my x centroid is equal to a x bar divided by the area. So it's the sum of the area times each x bar. So what I have here, the way I have it drawn is like each one of these, like area 1 has its centroid, right? Its centroid is 2/3 of the way over because it's a triangle. So it's 1/3 from the vertical side. A2 is right at the midpoint of its shape because it's a rectangle. A3 is up here, and vertically, same idea. You could probably figure that stuff out, right? But there's the equations. We just add up each area times its individual x bar divided by the total areas. It's almost like a weighted average. And then moment of inertia. Well, moment of inertia, we just have an equation. We're just going to plug it in. No reason to integrate. We're not going to have anything that's too crazy in this class. But the moment of inertia of a rectangle, which is our most common shape by far, is 1/12 BH cubed. And we'll use that so much, it'll be ingrained at some point in your mind. So when I'm adding these composite shapes, multiple shapes together, and I need the moment of inertia, we have this thing called parallel axis theorem, which is basically what's the moment of inertia of each shape plus AD squared, where A is the area of each one of the shapes and D is the distance from the common centroid that we're looking for. And I know that's a mouthful, so I think it just show best with an example. In this case, we want to find 2 things. We want to find Y bar, where is the centroid of those 2 shapes, and also what is the moment of inertia about that Y bar. So we just said Y bar was equal to the sum of our A Y bars over the sum of our areas. Oh, that's an A. So shape number 1, the way I have it listed, for area, I'm doing base times height each time because it just makes it more, it's kind of the same process we're going to use when we come up and start looking at our moment of inertia. So as long as you always put the base first, at least you're in the same order, you're not cubing the wrong thing. I know it's the same mathematical value, but so for shape 1, we have a base of 2, a height of 0.5. Y bar is our distance from some common axis. In this case, we're showing that it's right here at the bottom of it up to this point right there. Well, because we have 0.5 to get for the total height, then it's 0.25 to get halfway up. Plus that upper shape, its base is 0.5, its height is 1.25. Its Y bar to get to its individual centroid. So that Y bar shown there is like to the whole thing. This one would be like about here, I guess, right? So what is that distance? Well, I take that half of 1.25. So 1.25 over 2, right? But that only gets me to like here. Then I have to add in that last 0.5 to get the total height to the bottom. And then I just divide by the areas. So the same 2 times 0.5 plus 0.5 times 1.25. And I ended up with 0.58, what did I get? 65 inches. Cool. There's one thing I was looking for. Now let's find the moment of inertia. We said the equation for that is equal to the summation of the moment of inertia of each one of the shapes plus the area of each shape times this D squared, which is basically like the distance to get to that centroidal axis. So moment of inertia for shape 1, we have 1/12, its base is 2, its height is 0.5, and the equation was 1/12 BH cubed. Now what I'm doing is I'm coming up here and I'm just going back and saying, whoop, I went too far. I have base, height, and then this is going to have something to do with D, which we'll see in a little bit, but I have plus, for that, still that shape 1, AD squared. So the area is 2 times 0.5. What am I going to do about D? D is where I take this last value and I look at the value of the total centroidal axis. And what it's basically saying is, this is D. So I found this Y bar to be, what is it, 0.5865. Well, D is this distance right there, because I just found the moment of inertia of this entire shape, but now I have to move it up to here. So what is that D? The way I get there is I just take this particular centroidal distance, which is 0.25, subtract out that 0.5865 in either order because I'm squaring it. So let's see, we have 0.25 minus 0.5865, and that's the one we're squaring because that's AD squared. And once again, this is why I put it in order, because that last number will always be that D. I have one other shape, 1/12, base 0.5, height 1.25 cubed. I'm just looking up here. And then I say plus 0.5 times 1.25, that's the area, times this last little bit, which is this whole thing here. If you did that, I ended up with 1.125. So we have 1.125 minus this 0.5865 for the same reason we said earlier. Don't forget to square it. Punch it on to yield calculator. I'm up with 0.3967 units if you followed through, or inches to the fourth. So 1/12 BH cubed, I have a base, which is inches, and I have H cubed, which is inches cubed. And so I end up with inches to the fourth. All right, so that in a nutshell is the most important stuff you can get from statics that you should have for this class. Give the homework a shot. You have practice problems on a couple of these. I want to say there's a shared moment diagram. There's something with this guy, but regardless, in a nutshell, there's your review of statics. Thanks for tuning in, and I'll see y'all next time.